Okay, we'll continue. So usually you would run more than one model when doing a regression. You wouldn't just do one model and that's the end of it. So normally you or your supervisor want to run multiple models, and ideally you should check those for every single model that you do. Sometimes people only check it for their final model, but usually what you have in your reports are these hierarchical regression tables. So you start out very basic with one variable, and then you keep on adding variables, for example, to see if the effect survives after you control for a bunch of other variables. That's usually the way forward. So in this case, we're building a second model, and this time we're adding the percentage of women to see if that influences the prestige score as well. And you can see already that it's significant as well, and there's a negative effect. So a larger percentage of women in that job leads to low ratings of prestige. Okay. So what we want to do then is combine all that into some pretty tables to make those hierarchical regression tables. So don't worry about this. This is all the HTML output. This is Stargazer, which you might remember from some of the previous bits. We tell it which models to use, module education and LM education women. We can now specify the labels. So the dependent variable label should be prestige. And then the covariate labels, and these should map onto the variables that we have in our model. So that should be education, and we can say that's in years. And we can say women, that's in percentage. And we can actually also say we can pick from a variety of styles. We can pick the journal Demography or American Sociological Review. Unfortunately, because this was developed by social scientists, there is no APA type of template. So, but some of them come quite close to what you would need for an APA type of report. And this is sort of where it will live. So this will be an HTML table, and this will be having no header. So you can see if it has a header or no header. And so let's see if I can actually find that for you. So this is sort of what it will look like then. So this is a nice format table. Again, something which you can sort of drag and drop and get into your report. So you just do in your browser Command A or Control A, depending on your Windows or Mac, Control C, Control V, and you paste that into your report. And it has the coefficients with this type of star notation, like for the p-values. It has the r and the r squared. It tells you how many observations there are in the data. It has these f statistics, so it has all the bits and bobs that you care about. It has some nice labels for the model 1, model 2, and you can see how the coefficient then changes or doesn't change if you start adding things to your model. Yeah. So usually that's what people are looking for in this type of reports, not just a single regression, but a series of regressions and then seeing how the coefficients change. Yeah. Any questions so far? So again, hopefully I'm convincing you more and more that these are useful things to have and to do. So a sample write-up, for most of the things you wouldn't duplicate information, so my preference usually would be that you summarize everything in a table and you say, look at table X, and that describes this hierarchical regression on prestige. The first model showed a statistically significant positive effect of years of education on prestige. In the second model, the effect of education was upheld. You could look back and see the coefficient was roughly the same, became even slightly stronger after you controlled for the percentage of women. And you also found that the effective percentage of women was also statistically significant, right? And that you could still specify that was a negative effect or something. It depends what the focus is of your paper. If your focus is on this or on this, you would draw more out and say positive, negative effect, strong, weak effect, depending on whether something is a control variable or a variable of theoretical interest. But this is sort of a sample write-up as to how I would write up such results. Now, interpreting B coefficients, this should be a little bit familiar in the sense that what we have to do is we can use those things from our models to then make predictions. What would happen if you have 10% more women in that job? How does it affect the prestige rating? What happens if, on average, you have to study 2 more years for this job? How does it affect the prestige rating? So what we can do then is we first center everything, because it's usually good to look at shifts away from the mean. So that's why we do centering. And so you remember that this is how you do centering. This is something you've done in the first thing, and this will make more interpretable B coefficients. It doesn't change any of the significance testing. It will just make it more interpretable because now it's a shift away from the mean rather than a shift away from an absolute 0 point, like going from 0 years of education to 5 years. So centering means it's a shift away from the average education or the average percentage of women. So that's usually why we want to have centered coefficients. And later on, usually it's also important if you calculate interaction variables. So usually, sometimes people center their variables. So this is just centering everything, centering also our dependence, so you can center everything, and then we can run the same type of model. And then we can interpret, so this is now a centered model, where it's everything ends with this type of cent at the end. And so that means that we're now looking at shifts away from the average in X and in Y, yeah? Rather than absolute shifts. So, what you can then see is that you can use that to do some very basic shifts. So if you do like 2 years of extra education, that's an increase of 10.86 in prestige scores, all else being equal. Remember, for all else being equal in the model. So that's basically 2 times this value, like this would be a 3. So that's how I get to 10.86. So a shift of 2 years away from the mean would boost your prestige ratings with around 11 points. Yeah. Similarly, if you have a 10% shift of women, that would be a decrease of around 0.93. And we know that because we shift the decimal by 1. Yeah, so this is a factor 10. So that means E minus 0.1 rather than 0.2. That's how I get to 0.93. So you can use that to make predictions and say what happens if we shift by 5% or 10% or 20% or in terms of years. So you can use the regression models to make guesses as happen if you change one variable compared to another variable. Does everybody understand what the use of this is? This is also something you're going to have to practice in your exercises and in your assignments. And you can see that if you look very closely, it doesn't change any of the significance testing. It just makes it more interpretable that there are shifts away now from the mean rather than shifts away from absolute 0 point. Now, the other thing is that we want to sometimes have everything on a scale, so we can say this is a strong relationship or a weak relationship. So you remember that there's a difference between unstandardized coefficients and standardized coefficients, like B's versus betas. Yeah, that should ring a bell. And betas are nothing more than standardized B, so we can z-score everything. So remember everything, we can put everything into a normal distribution, and then from a normal distribution, a shift of 1 unit is a shift away in 1 standard deviation. Yeah. So that puts everything on the same scale. There's lots of debate among statisticians whether you should report the unstandardized or the standardized coefficients. It depends also what your goal is. If you're making predictions about what happens if there's 2 years more education, then this is more intuitive. If you're interested in comparing the strengths of effects, then betas are more useful to say this is a strong effect and this is a weak effect. Yeah, they serve different purposes. So, but you should remember that a shift of 1 in a beta means a shift of 1 standard deviation. So if your beta is 1, that means you shift 1 standard deviation in y. Yeah. So if you shift 1 standard deviation in education, it means you shift 0.85 in prestige score standard deviation. Yeah. So the way we do this is I've been lazy here. Rather than making a new variable, I've done it within this type of formula. But you could, again, make your own standardized scores and then put them in here. But you can also call scale directly and say, scale this variable, scale that variable. And then what the key point here is that you have to drop the intercept, because you remember, there is no intercept if you do the standardization model. Yeah, so if you do calculate the betas, then we no longer have an estimate for the intercept, which tells us how much up or down we're going. We're really just interested in comparing the effects. So -1 will drop the intercept from our model. Yeah, so you can see in this model there is no intercept anymore, only the scale education. That's the beta coefficient. Okay. So if you standardize your dependent and your independent variable, then we have beta scores. Again, none of this will affect conclusions typically about significance. It will only affect the interpretation of the coefficients. Everybody with me? Yeah. So the alternative is to, if you think that's too clumsy to do, we have a package which helps us with it, which is cont'd, and we can just say lm.beta, and we'll give you the beta coefficient for that model. Yeah. So if you could scale it, or you could use this lm.beta beast to sort of calculate the coefficients for you. Now, as I recall, and as I keep on repeating, you can bootstrap everything. And again, this is sort of a robustness check to see how robust your findings are. And I won't go through this code entirely because it's again the similar type of code that we had when we were doing the t-test or when we were doing these other things, when we were bootstrapping things. So basically, we can call within this object, we can find the position of the coefficient, and that would be the second one because this is this is one which has unstandardized coefficients. So the first position would be the intercept from the output. You remember? The second one would be the coefficient of education. So education is in position 2. So this is calling the coefficient and it's doing, then we're going to do that 1,000 or 10,000 times every single time to get that coefficient. And then we can look at all those coefficients. So just go back and look over the code for a t-test. But for any object, we can basically tell the computer to do it over and over, like draw a random sample, do it at 1,000 or 10,000 times, and then see how much variability there is in the estimate of these coefficients. Yeah. And we can then calculate a 95% confidence interval about coefficients. So just go back over the code if you don't understand it and go back to the week where we talked about t-tests. But it's basically the same type of premise. So we generate an object. In this case, it's a regression object. And then we call something from it over and over and over. Yeah. So in week 1 or week 2, it was the t-test. But you can do this for any type of metric. Yeah. So, and then to make it replicable, we put 666 or any type of number you like, and then you can look at the results. So this is the original coefficient and the standard error. And so what we can then look is at the 95% confidence interval. I've only learned to appreciate this recently. You can get very minor differences if you don't put in a seed here as well, because it will correct some of the things. More or less, it's only to the second or the third decimal. So, but if you want to make it 100% replicable, you also put set seed in here, yeah. And you can see that that coefficient, that 5.42 coefficient, that has a 95% confidence interval. If you don't say which other ones you want, then by default it's going to give you the 95% confidence interval. It has a 95% bias corrected accelerated confidence interval going from 4.86 to 5.99. So if you were to basically do your study 1,000 or 10,000 times, then most of the coefficients would fall within this interval. Yeah, that's not 100%, but yeah. Any questions? So we've talked about regression. I've shown you how to do your basics to how to standardize and understandardize, but sometimes you will have a dichotomous outcome. You'll have something like dead or alive, lost weight, didn't lose weight, cured, not cured, cancer, no cancer. You'll have some type of dichotomous outcome measure. And so we cannot use OLS regression because it violates this assumption of normality, right? So if you plot this data, you'll just have 2 categories. So we can't really use our ordinary least squares regression. Now, in a very clever way, we can. And so by using a transformation, we can turn everything into odds ratios. So because we can convert things into proportion and to odds, and they will behave as if they were normal. And so the trick here is that we calculate everything based on log odds, which are linear. And then using that calculations, we can then convert back to see what the effects would be. That's in a nutshell. Like, we could have several lectures on logistic regression, but in a nutshell, that's all you have to know. It's sort of a clever trick, which has been applied, I think, since Pearson even, to get something which is dichotomous to behave linearly. Yeah. And so you can read references for full explanation in the text at the end. So, because of that, actually, logistic regression is more robust to some of the issues which you might have with regression. So, some of the assumptions that you would check for regression or for ANOVA or MANOVA don't apply here. So, you still have to have correct coding of your dependent variable. So, if your research was quite sloppy in coding who's dead or who's alive, then that's going to influence the conclusions which you're going to get. So, it's assuming no measurement error. Again, yes, it's assuming that there isn't, for example, people weren't very much more accurate in coding deaths than people were alive, for example. Yeah? So that's the assumption that goes into it. It's assuming that all the relevant variables are included, so that you haven't missed any variables, and so that you've not over or underfitted your model. Yeah. So you've not, you've just selected all the variables which predict, for example, whether people die on the Titanic, and not missed any. Again, as before, you should have independent observations. When coming to multi-level, sometimes this will not be possible because, for example, you're looking at whether people pass uni, and people are clustered in degrees, and so they might be very good at psychology, and there might be something specific about psychology, but not about engineering. And so you want to cluster the non-independence, the fact that your psychology students are more similar to, let's say, engineering students. And in order to model that, we're going to use multi-level models, but I'll get to that in the end. And so now linearity still applies, but it's linearity between the log odds and your independent variable. So you should still have this linear type association, but it's relaxed because it's not between the 0-1 type of thing, but your log odds should relate linearly to your independent variable. I come across very, very few people who ever test this, so don't worry too much about this. And sample size, these tend to be data-hungry methods. And so depending on who you talk to, like some say that you need 10 per predictor variable. So if you have a data set with just 10 cases, then you could fit one variable. If you have one with 20 or 200, then you could fit many more variables, yeah? And others would say that you need to go up to 30 per estimate. And that's based on like estimations will become better if you have more data behind it, yeah? So we'll be less likely to make some errors. And the reason for that is because it's slightly different, and you'll see also from the output, ordinarily squares, you can think of it as doing a single shot. It's a single shot that's trying to fit this line through the points. And here we're going to use something which is called likelihood estimation, which is an algorithm. And that means that our second best guess would still be sort of okay. So it operates in a different way than when you were to estimate your regression line. Your regression line is simply an equation. It's a single shot. And here we're going to use an algorithm to sort of estimate those coefficients for us. And the idea would be that the algorithm converges, and the second best estimate would still be sort of okay. So that's why many of these assumptions are relaxed, because it's not a single shot anymore. It's relying on an algorithm based on maximum likelihood to do those estimations. Yeah. So some argue that logistic regression doesn't require any assumption checks, and that's in part because it's this algorithmic way of doing this. So it's a long story, but maximum likelihood estimation does a lot better than ordinary squares estimation. And so what they say is that instead of worrying too much about your assumptions post hoc, you should really think, have you measured all the variables that you need to measure? Is everything well defined? So are there no coding errors, or are people not more likely to be coded as dead or alive? So is that consistent? And you need to think about those things before you run the model. And so, and as always, I'm going to repeat this over and over. You can bootstrap everything, so you can test how robust your model is by doing that 10,000 times and seeing how much the coefficients change. If they start moving all over the place, then you probably have lots of uncertainty, and that probably isn't a very robust finding. Any questions? So it's a little bit more relaxed here. You could still check some of these things, but it's slightly different. We're going to look at a new data set. This is a data set from Pima Indians, and this is a health-based data set. It's living in NL Bench, and we can use SkimR, or you could use your other favorite package to sort of look at the distribution of these variables. So our dependent variable will be diabetes, so which is yes, no. And then you have some variables like age, or glucose level, or body mass, or insulin level, and that's what's living in this data. So it has 9 variables and 768 cases, and it's basically a data set on women aged over 21. And so this looks similar to what we had for regression, but the big difference now is that we have a G, and that G stands for generalized, because that means here we do binomial, but we could do many other families. You could do Poisson, you could do all sorts of other families, and you could do all sorts of other families with this generalized linear model. Yeah. And so the G is just GLM, and again, you sort of remember the formula. It's dependent variable, independent variable, the data that we call, and in this case, we have to say what type of family model are we using. And because it's 0-1, it's binomial. If you were to have multiple things, like not 0-1, but 0-1, 2, 3, for example, or multiple categories, then binomial wouldn't be working for you. Yeah. And if you were to check, I think you can just put Gaussian, and that would be the same as your ordinary squares regression model, but estimated in a different way, because that's for a normally distributed dependent variable. So here I built 2 of those models. The first one just has mass, and the other one has age as well. Yeah. So, and then this is a summary. It again prints the formula. It gives you the residuals, and then it will give you some blurbs, which we'll run to later. But the key thing is not to worry about too much about those, but to look at the significance estimates for your parameters to see if you get a significant effect or not. This is for the two things, so you can see that both mass and both age are significant in these models. So, yeah, so they will influence the degree to which women are diagnosed with diabetes in this data set. So summary gives you the parameter estimates and the associated tests, and in literature they're known as wall tests. So these are wall tests. So if you ever come across a wall test, that's a wall test. But simulations or statisticians have shown that a likelihood ratio test does better if you have smaller samples. So these tests, these wall tests, don't do very well if you don't have a lot of cases. So if that's you, then you might want to do likelihood ratio tests. And you should be concerned if the conclusions start differing quite a bit, because that isn't good news. So ideally, you get the same conclusions if you do a likelihood ratio test or if you look at the parameter estimates. Yeah. But this is the golden standard, this likelihood ratio test. So how do you go about doing that? And this is using our ANOVA command again, log1, that's the model, and then the test is known as a chi-square because it's a chi-square distributed test. And then it will say this type of significance, and this is a chi-square distribution. And in this case, we have the same conclusion, it's highly significant. As you might expect, body mass is associated with being diagnosed as diabetic or not diabetic in this sample. Yeah? So no surprises there. Any questions? We can do the same for our second model. So here we have two tests. And again, in this case, we're not going to find very many differences because we have quite a big data set. We have 786 or 768, I think 768 it was, cases. That number doesn't add up to 768, presumably because there's missings which have been removed in the analyses. Okay? So these are these likelihood ratio tests. So if your supervisor asks for a likelihood ratio test, this is how you would calculate them. Now, these coefficients, they're not really interpretable. So that 0.1, if we go back and look, 0.107, that's a log odds. So it's a logarithmic transformation of the odds. So they're not really interpretable because it's a really weird mathematical transformation to do so. So what we can do is we can take the exponential and then they become interpretable. Yeah. So you have to remember that what we're doing here is we're looking at the association between the log odds and the independent variable in this type of models. Yeah. So we can take the exponential to solve them. And we can do that again via package. So we can say odds ratio. And we can also then even say what happens if you have a shift of 5 units in mass. And so in this case, I think mass is probably, I don't know by heart, but I think it's BMI. It's the same. And so you can have, so that's not useful if you have things which are categorically coded, because then it doesn't make sense to have a shift of 5 units. But for mass, we can do this. And note that you might want to center your data beforehand, which I haven't done, because then it's a shift 5 units away from the mean. In this case, it's just an absolute shift of 5 units from the absolute zero of BMI. Yeah. So what you then get is you get this odds ratio, 1.67, and again, it will calculate for you the 95% confidence interval of this odds ratio. Yeah. And you can. This is the one below is the one for where you have two shifts. So this is log 2. So here we shift age with 1 year and mass with 5 years. 5 units, sorry, 5 units. Yeah, does everybody sort of understand? So what is an odds ratio? This is an alternative way of doing it. Again, there's many different ways in which you could do it in R. I think hopefully you see that it sort of matches closely, but it will match or not match depending on whether things are included or not. If we go back in model 2, so in this case it will not match because I didn't tell it's 5 units, so this is a shift of 1 unit. And so in this case it's a shift of 5 units, so you will get a bigger value. So these are the odds ratios, and now the question is what do you mean, and how would you write it up in your report? So in model 2, the odds of having diabetes versus not having diabetes. So odds are, if you know anything about gambling, odds are always an event versus not the event happening. Yeah. So you're betting on somebody becoming president versus somebody not becoming a president. So, and then you're able to say the odds is 20-1 that, for example, Obama will run again for president, or 200-1. So it's, if you ever gamble, it's quite intuitive to think of odds because it's likely of an event of the event not happening. Yeah. So the odds of having diabetes versus not having diabetes is 1.1 times larger when BMI increases with 1 unit. And that's for that second model. So that's this value while controlling for the other thing in this model. Yeah. So as you shift 1 unit in BMI, your odds increase with this factor. Yeah. So depending on whether that's large or small, you'll have to play around and calculate some examples for yourself to see if you think that's a really big or really small shift. Yeah. So odds ratios, for example, of 3 or 10, that would seem like very big shifts. Again, it will depend if you shift with 1 unit or with 5 units or 10 units. So you would have to think as to what is a reasonable shift to have in that thing to see how the odds shift as you do that. Yeah. And depending on what you put in there, you will tell a very terrifying story or a very unterrifying story. Yeah? So if you shift with 1 unit or 5 units or 10 units or 1 standard deviation, you'll get very large or very small shifts in the odds of you having diabetes going up. Yeah. So does everybody sort of understand this concept of odds ratios? Yeah. It's the likelihood of an event happening, in this case, diabetes versus no diabetes, and how that shifts according to a variable. So odds ratio, the clue is in the name, it's basically 2 odds divided by one another and seeing how the shift happens when you manipulate one variable or one variable changes. Yeah, so that's how you sort of would write it up. And those values are nothing more, nothing less than what I got here from this table, like the 95% confidence interval. So, because psychologists and everybody else loves R squared, so you also want to have something which is like R squared. There's lots of debates on whether you should calculate this, because now the data aren't really linear. It's a little bit fudging it to some degree because you have to figure out a way in which you can calculate this that would still make sense. There's lots of debates, but my favorite is Nagel-Kirk R squared. Like, so again, some statisticians say that perhaps you shouldn't calculate these because they come with some problems, and you can do Nagel-Kirk R squared, and this is like whether you would like to restrict the observations to, for example, the ones that are missing or not missing. So that's the second bit to it. Again, you can read all the codes as you go along. And so this is from the R companion package. And this model, Nagel-Kirk would explain around 13% of variance in our things. But depending on which one you pick, you will get large or small numbers. Bear in mind, like some of these are not constrained. They don't have, like, an R squared can go from 0 to 1. Like explaining 100% of variance would be an R squared of 1. But some of these don't have natural limits, so they can go above 1. So that makes them harder to interpret. Yeah. That also probably pushes the value down. Nagel-Kirk R squared will be constrained between 0 and 1. And again, you can read a lot more if you click that paper and do a little bit of your own digging to find out how these R squareds work. Yeah, so these refer to the model, and this is the first model. Again, we can try and get a nice table from everything. So in this case, we want to have a table with the odds ratios because the coefficients themselves aren't they don't mean as much because they're log odds, so they're very counterintuitive to work with. So what we do is we call Stargazer, we call our models, we say these are the covariates, so BMI and age rather than mass, for example. We want to drop the constant because the constant isn't really interpretable, it's not of use to us. And then we can transform the coefficients. So if we do this, applied.cov, this will make the coefficients exponential. Yeah. And then we can we don't want to do that for because we do this is set to false and this is set to false because otherwise it will do an exponential transformation also for our t values and our p values and do that, and that's not what we want. So what we can do is still report the star style significance. But if you just would leave those, then those values wouldn't likely be correct because you applied some transformation to your models. And in this case, I'm going for the lovely journal American Sociological Review, and the out thing will be logistic.htm, and I again say it shouldn't have a header. So what will that look like? It will look something like this, hopefully. So these, in this case, we just have the odds ratios with the star notation. We don't have the 95% confidence intervals or standard errors or something like that. Just the star notation, but it will have printed the p-values with the star notation, and it will have printed the likelihood, which some people will use to calculate things. And AIC, I've told you a little bit about this perhaps already, but more will follow. This is a measure for how good a fit the model is, and you want lower values. So in this case, you see if you add something significant to it, this value goes down, and then you have a better fitting model. I'll talk more about AIC and these fit criteria when we get to structured equation models and we talk about multi-level models. But for now, that's all you have to know. So a nice little summary from what is going on there. Yeah. Again, this saves you the time of having to do it manually via SPSS, copying and pasting, faffing around with all sorts of things to make it look pretty. This is, in essence, once you've done it, a very easy way to generate tables for your report if you have to do lots of these. Any questions so far? Okay, so again, sample write-up. You would refer back to the table. Table X shows the key results for a hierarchical logistic regression analysis. In model 1, there was a statistically significant effect of BMI on having diabetes, and then if you're 100%, we'd say on having diabetes or not, because, but I've left that out. I report the chi-square values, and those chi-square values would report back to the log likelihood ratio test that I talked to you about before. And in model 2, there was a significant effect after accounting for BMI as well for age. And those chi-square values correspond to the likelihood ratio test, which I've shown you. You can also calculate them for the overall module, and you might want to add pseudo r squared. And then when you go on, you would describe the odds ratio. So you would say the effect is this big. So if we shift 5 units in BMI, it means that X amount of more people, their odds of getting diabetes go up by a factor X. Yeah. So this is just the statistical significance reporting. Then you would illustrate it either graphically, saying if you shift this much, this is what happens, or you would explain it verbally. Now, if it's continuous, you can plot the odds ratio, so you can see how it shifts if you move from things, so you can see how bad it becomes and how the odds ratios shift. But it's quite difficult to do that for categorical variables, so we're going to try and look at some alternatives, and we're going to look at GG Mosaic if you want to do it in ggplot. But the VCD package allows you to visualize what it would mean to have categorical data. So how do you visualize these type of results is what we're after here. Yeah. So because this data set doesn't have any categorical variables, I'm going to do something really bad and make some as I go along. So what I did is I put in a clinical cut point for obese, which is at 30, and I say obese, no, yes, and then I make one for nulli gravata is a very scientific way to say whether somebody was ever pregnant or not, and I make one that says whether they were never pregnant or ever pregnant from that code. Yeah, so you can have a look, and this is using mutate and then putting in breaks and cutting to get the variables to do that. Yeah. So here I generate categorical variables, and that's just for ease of illustration because this data set doesn't have any nice categorical variables to play with. So we can pick some colors. So by now you can all pick your favorite colors. In this case, I picked some from our color brewer. I picked from set 3, and I picked 2 colors. And I call it colors because that's easy to store somewhere and then call it back later. Yeah. So you can store any object. You can store colors. You can store values. You can store everything if you want to in R. Now the fill colors, like these, like you have to think how many quadrants would there be filled, and so what type of plot will it look like. And so in this case, we need 4 of each to fill up that quadrant. Yeah. Then we make a mosaic plot. This is mosaic. This is our dependent variable diabetes, and then nulli gravata and obese, yes, no. And then in some cases you'll have zeros, but in this case we don't, so we say zero size is 0. The data, how to fill the parameters, so which type of course to use, that's the gpar type of thing, so that's making sure that we use this type of course, whether we want the legend and whether we want to have labeling, and we can say use the labeling values that you have. Yeah. Okay. And then you get something like this, and this quite easily supposedly shows you how many cases there are with diabetes. So in this case, this is a positive test for diabetes, this is a negative test for diabetes, and you could see that especially if you were ever pregnant, for example, in that group, you can compare all the different groups by looking at it in graphical type of thing. You can look at the size of the pie to sort of see how it plays out. Yeah. So especially if you were never pregnant, then you could see some changes there. Yeah. Any questions? So it should stand out that you are within these. So if you are diagnosed with diabetes, the likelihood that you are obese is also quite high compared to not being obese. Yeah. So this plot is showing a lot of information, so it might take some time to wrap your head around, but it's a nice visualization. You can think of it as a slice of pie and see how all the odds are, all the cases are divided in this way. So that's how you plot categorical data, and as part of your exercise and assignment, is something you'll do as well. This brings me, I'm good on time today. Woohoo! So this brings me to the exercise. Alex has just pointed me to like a fun fact that one of the links doesn't work because even though the code is correct, it doesn't place a bracket. I'll come to that in a bit. For the exercise, I'd like you to load last week's salary data set, which you by now are familiar with, which has like associate professors and assistant professors in the US and how much money they earn. I would like you to calculate the Spearman and Pearson correlation between years since PhD and their monthly salary. Hopefully you will still have that from the other time. Otherwise, you again have to have a look at whether you have to calculate some things. You conduct a significance test and pick one and discuss the outcome. So write it up as you would do in a report. Then I would like you to build a hierarchical regression model. In step 1, use monthly salary as the dependent and year since PhD as the independent variable. In step 2, add gender, keep all the variables from step 1. In step 3, add rank and keep all the variables from step 3. Yeah, export everything as this type of table that we had. So you're going to use Stargazer to make a little pretty table. Rather than doing it for all the models, just for the final model, test the assumptions. How would you combat any of these issues so that you don't have to like run all these complex econometrics tests, but just report what you would do if you were to have a violation, how you would solve it. And then, oh, this is not, there should be space here because it's the beta, so it should be the symbol beta. I'll try and fix that. Calculate the standardized coefficients for model 1, for the first model. Interpret the coefficient, so what does it mean to shift 1 unit? Bootstrap this coefficient, so you can bootstrap everything, so you can also bootstrap that. And report as you would do in a paper. What does the final model predict in terms of monthly salary shifts when you shift away being 3 years post PhD? So how big a shift does that lead to in income? And then this is for the last bit for the categorical data. Load to the correct package, load to German credit data set. You can find out more here, but this link is broken, so you need to put an additional bracket at the end so I can show you. So if I go here, then it will say it's not there, but if you do this, it will magically appear. And then, and even though it's correct in my code, this is one of the quirks which I have to hammer out why it doesn't link to that. I think it's something to do with Google Chrome or some browsers not liking you to have brackets in links, which will take you to viruses and things like that. So I'll see if I can fix that. Otherwise, I'll put in another link. So this data set is ancient like me, and so it has data from credit scores in Deutsche Mark, which was before the euro, and so it's a famous machine learning data set. So it has 1,000 cases and 62 variables, and you want to explore some of the descriptive statistics to see what's in that data set. Make a correlation plot for 10 of the continuous variables. So you look for some continuous variables in that. Make a little correlation plot with that. Export a correlation matrix. Then you conduct a hierarchical logistic regression on class, and class will tell you whether they are good or bad people in terms of credit scores, whether they pay up or not. In step 1, add the amounts. In step 2, add credit history and pay duly. In step 3, add age. In step 4, add whether they have a telephone or not. and export that data as results. And then choose some categorical variables and make this beautiful mosaic plot, which I did. Calculate the odds ratios for model 4. That's the final model with telephone in it. And what does a shift mean in 1,000 Deutsche Mark in credit states for model 4? So if you shift 1,000 in Deutsche Mark, how does it change your credit score? And then you can make a beautiful GJ mosaic plot, so not using VCD, but figure out on your own how to make that. And then I've not talked to you about receiver operating curves or sensitivity specificity, but if you want to, you can make one of those for those credit data as well and do something fancy along those lines. Any questions? So the exercise is also going to ramp up a bit. Don't worry if you can't do the bonuses, because they're quite hard to do, but play around with those. Any questions or things which were unclear? So I think perhaps today for logistic regression was new to you, like regression and correlation should still be somewhat familiar. So next week we'll have ANOVA and 2x2 interactions. We'll look at categorical interactions, continuous interactions, and what they all mean. And then we'll have a break after that for academic development week. Any questions, burning questions or things which are unclear? So after next week, you can all finish your assignments and like have lots of time off, so or not. I'll leave it there. I think Alex and Sarah will be around, and yeah, there might be some peculiarities with loading the German credit data, but Alex will tell you about those if you run into problems with like loading the German credit data. But perhaps you've managed in the end by using the correct. Yeah. It works within correct. Yeah. Yeah, the way we did it. Okay, that's the most important bit. Okay. If you have no questions, then